Now we have the Earth and the Moon. Mass m sub e for Earth, mass capital M sub moon for the Moon. And we have a mass here at some point, which is ostensibly the point at which the gravitational attraction of that mass to the Moon is equal to its gravitational attraction to the Earth. So that this is the unique point between the Earth and the Moon where we have no net force due to the two planets. Now, theoretically, if we park something stationary right here, it would stay there. But the Moon's moving, all kinds of things are happening, so it gets a little more complicated than that. But it's a position that we can sort of maintain if we match the orbital frequency with the orbital frequency of the Moon. We could kind of park something at that position. We probably have to adjust its position a little bit every once in a while, but if we do it well, we wouldn't have to do a whole lot of adjustment. Okay, now I call the distance from here to here R equal gravity. That's EQ capital G, equal gravity. Okay, so R EQG stands for the distance from the center of the Earth at which we experience equal gravitational force to the Earth and to the Moon. Then, at that distance, the force exerted by the Earth is big G, mass of the Earth, times the mass, whatever it is that we're parking there, divided by the square root of R equal G, by the square of R equal G. I think I might have said square root. Okay? Then, the force exerted by the Moon is what? Well, I'm letting R sep stand for the separation of the Earth and the Moon, the average separation, around 250,000 miles, 400,000 kilometers, that neighborhood. The orbit of the Moon is a little bit eccentric, so we don't have one fixed distance. Anyhow, the force exerted by the Moon then is, again, big G times the mass of the Moon times the mass of the object here, divided by the square of this distance. Well, this distance is just what I call R sep minus R equal G. So we do R sep minus R equal G quantity squared. And again, that's the force of the Moon. Now, if they're equal, well then, this expression equals this expression. And if we set them equal, we've got a big G and a little m in the numerator of each. Those can be easily divided out, and that's going to leave us mass of the Earth over R equal G squared, and mass of the Moon over the difference of these two distances squared. That's an equation that we can solve for R sep minus R equal G. And I believe that if we, okay, we can rearrange this to give us this over this, just this in the numerator here, and then this in the denominator over here, and we get that by multiplying both sides by this quantity, and then dividing both sides by this quantity. We get this. Mass of the Moon over mass of the Earth is given to be 1 over 14. Now that's not absolutely correct to any number of significant figures, but that's probably the closest whole number we can put in the, it's the reciprocal of the closest whole number that we could use to approximate that. Okay, so we have this equals this, 1/14. We take the square root of both sides, just leaving this intermediate expression out, and we get that R sep minus R equal G is R equal G times the square root of 1/14. And from this, we do a little more rearranging R equal G over on this side, and then we factor out an R equal G. We get an R equal G times 1 plus the square root of 1/14, and that's what is going to equal R sep. So R sep is going to be, R equal G is going to be R sep divided by that sum. And if we approximate this, I think we get something a little under 0.8 times R sep. If the 1/14 is accurate, this will be maybe 0.78 or 0.79 times R sep. meaning that this point is about 80% of the way from the Earth to the moon. That's about the way I've got it drawn.